Assalamu alaikum everyone. Today we are going to start the article 9.5 feedback compensation. So two more topics left actually. I already uploaded the video on the previous topic. I'm not sure whether you have gone through or not. I hope you have gone through. Now let us continue with this one. So this is an alternative approach to the cascade compensation. So generalized block diagram for this one is something like this. You can have your input signal, then you'll have a gain parameter. So generally the gain that we vary k is this one, and then you have another summing junction, and that will go to the main plant. So in the main plant also there may be another gain k1, and then it will go to the plant itself. G1 is our plant. So this is a more generic configuration, but some of the parameter may not be available in some of the control system. Okay, so then you have maybe another gain adjustment G2S. Okay, so in cases you'll see some of them are not available. So then you have your feedback that is coming to the plant is KF HCS, and then your overall transfer feedback is actually unity feedback. So we have two loops. The inner one is known as minor loop, and the outer one is the unity feedback one is known as major loop. Okay, so you have your input. Feedback is always negative. Then you have your output. So this is a more general kind of feedback compensation, where actually compensation is done here. And these parameters may or may not be there. So if you have K, maybe 1 unity, as well as G1 unity, either of them or both of them. So based on that, few other configuration you can derive from this generic configuration. Okay, so why feedback is necessary? In some cases, our control system has a huge noise signal, which can be amplified if you put it in the cascade zone. So that is why we have to, in those cases, we actually have to go for the feedback compensation. The cascade compensation is not possible if the system has a huge number of measuring noises, which can be escalated if you put in the forward path. This is one thing. And what are the advantage of this one? Even though we have to admit that feedback compensation is complicated, designing is complicated than the cascade compensation. So this is complicated, but it has advantage over the cascade compensation, that it is this design is faster. So the minor loop and the major loop can be designed separately, and if the minor loop is faster than the major loop, then we can actually isolate the two control system design. So basically minor loop will be designed separately from the major loop. Okay, so feedback compensation also gives you another advantage, that is that sometimes we need amplification of our feedback signal. But since we have, in this case, we are taking the our signal from the output. So that is why in most cases actually de-amplification is needed, or actually a high power level signal here will be actually reduced by this one, and then it will go to the low power level. So this is one of the side advantage, nothing major. So Example of this one is one of them is called rate control system. So in case of position control system, so in rate control system, what we have is actually KFHCS is just a F is the constant and S. So S is nothing but d by dt. So basically, for the rate control system, the HCS can be replaced by S, and for a tachometer or for rate control system, the angular velocity can be detected. Okay, so the output voltage will be proportional to the angular velocity in case of the tachometer. So basically, KFS, then you have your output voltage, and input was actually position theta. So theta, if it is differentiated, then you're getting velocity. Then from the velocity, with the transducer, we are getting actually output voltage. So how actual system looks like? So basically, actual system example is something like this. Now you have the gain K here. Okay, so for the motor position control system, so if you were to take the feedback as a rate feedback, okay, so this is your K1, then you have the plant, maybe the motor, G1S. Then in this case, basically, you don't have G2S. So G2S is in most cases actually amplifying factor. So if your plant needs additional voltage or power, then we actually do the amplification. So this is your rate control system. Okay. And also for the cell line, you're going to go to the unity feedback. So this is your example of your feedback control system using the rate control system. So now, what is the design procedure here in the feedback? So bottom line, the simplified idea is to figure out what is the value of your K, K1, and in the feedback gain KF. Okay, so you have to figure out this parameter based on of your choice of your HCS. Like in the rate control system, it is actually S, but it can be any other function. So you have to choose this one, and based on that, you have to figure out what is the value of K, K1, and KF. And for going for your feedback control design, feedback compensation design, there is two approach. The first approach is actually similar to the cascade compensation. So we have two approach. Okay, so first approach is similar to cascade. Okay, so the way we actually do the cascade compensation is actually you have to figure out what is G of S, H of S. Okay, so or in more general, if you want to say, then actually you have to find out 1 plus K G of S, H of S. So if you put the K inside the G of S, H of S, then actually we are looking for this parameter. Based on this parameter or the loop gain, this one is also known as loop gain. Okay, so based on this loop gain, you have to draw the root locus. So similar idea. So what is the difference? In the previous case, in the cascade, what we have done here is we have plotted the root locus based on your G of S, H of S. That is different that your H of S was 1. Here, to modify the root locus, what we have done, we have added poles and zeros, to have our desired performance, zeros in the cascade, or actually we have included in series with G of S. So we have changed G of S, poles of G of S is added, and we actually design our compensation. Now, what will be the modification here? Modification is instead of G of S, actually we'll be changing the poles and zeros of each of S here. So we'll be adding poles and zeros here. And this is how we are going to reshape or the root locus or moving towards the desired position. So we have to make sure that our root locus goes through the desired position. Okay, so this is the difference, but more or less similar idea. You have to find out the loop gain, G of S, H of S, And based of then, based of it, you have to draw the root locus, and after drawing the root locus, to go through the desired point, actually you have to add pole and 0 to h of s, not to g of s. That's it. So this is your approach one. And your second approach is designing separately. So minor loop is your feedback loop. So you design it separately, then you go for designing to major loop. So major loop, as you have already noticed, that major loop is nothing but unity feedback. So basically, you design the gain kf there, and then you design the gain k here. Okay. Finally, you have to adjust the gain k1. So bottom line is this. So two different approaches. So let us start with the first approach. So in the first approach, we have to actually have to start with this block diagram again. So that is why let us try to simplify this block diagram. So if we try to simplify this block diagram, then what we are going to get is, because we have to find out what is g of s and h of s, because based on that, we have to draw the root locus and we have to start designing it. So this is the first approach. Okay, see detail of the first approach. So what we are going to do here is we are going to insert this one here, and also we are going to insert this one here, and then this two parameter has to be divided with this one. Okay, so this is block diagram reduction again. So basically what we are going to get here is if you insert both of them together, so combined gain will be k, k1, g1s, g2s. Okay, so then feedback will be kf hcs divided by k and g2s, because this feedback should not be multiplied by that two parameter. So that is why we're actually dividing with it. Then we also have, don't forget about your negative feedback. Okay. So now what do you know? This is actually 1. So 1 plus this parameter should be there, isn't it? So let us simplify further. So what we are going to get here is I'm just making it quicker. So you just put the signs and input output parameters by yourself. Okay. Now, so what you are going to get here is K, K1, G1S, G2S. So the common one, so 1 plus that parameter. So basically it will be KF HCS plus KG2S divided by KG2S. Okay. So what was our target? Our target was to figure out what is G of S and what is H of S. Previously, H of S was 1 in case of the cascade, but here our H of S is actually have some actually finite dynamic, some dynamic function. Dynamic function, don't need to worry about the dynamic function, is actually in terms of S. Whenever you have S, either you have integration or differentiation, so it makes it dynamic nature. Okay, so now we have G of S, H of S. So previously, if there was no feedback, so what should have been our G of S, H of S is simply it was a unity feedback. So without feedback, our G of S, H of S should have been something like this. K, K1, G1S, G2S. Okay, but this is without feedback. Without feedback. Now, because of the feedback, what is our G of S, H of S? So with feedback, we have G of S, H of S equal to, just multiply both of them. So if you multiply both of them, so this parameter will be cancelled. This will be gone. So what will be left is K1 G1S, and then you have KF HCS plus K G2S. So now if you compare these two, so ignore the gain factor, so they're just magnitudes. So what we are going to see is that in the feedback, this one is been replaced by this one because of the feedback. So in without feedback, we have to compensate at pollen 0 here, and now we have to actually add pollen 0 here. Okay, so this is the difference. And also you have to be careful that the 0 of what happens to 0 of H of S. So H of S is nothing but our KFHCS plus KG2S divided by KG2S. So we want to see what happens to the 0. Actually, this 0 actually goes to the closed loop transfer function, or it is just a 0 of H of S, but it doesn't transmit to the closed loop. So this is what we are going to see while we are solving the problem. So try to keep it in mind. Okay, so or I can actually directly figure it out what will be happening with 0. So just find out what will be your closed loop transfer function. Closed loop transfer function is G of S divided by 1 plus G of S H of S. Okay, so we already know what is G of S. So it is basically K1 G1S G2S and multiplication of 1 plus G of S H of S is also K, K1 G1 K1 G1S, then you have KF HCS plus okay, so K G2S. So why we're saying that this is we have a 0 of this one is not actually transmitted here, so this is not present here. Okay, so 0 of your HS is actually not a 0 of PS. Okay, in the last while we were discussing the cascade compensation, actually if you insert the 0 here, so that 0 was actually transmitted here. Okay, so this is the difference with your feedback compensation. So we'll be seeing this phenomena in detail with while we are trying to solve the problem. Okay, so what is the advantage or disadvantage of 0 not being here? So if you had a 0 here, okay, so if you had a 0 here, so there is a possibility of pole 0 cancellation. Okay, so which is not possible in case of the feedback, especially this kind of feedback, because of the fact that this 0 is 0 that you are introducing here is not reflected here. So the pole 0 cancellation that is not possible, because one of the criteria was for second order approximation is to have pole 0 cancellation. So which is difficult to achieve for this kind of feedback because of the fact that the 0 of the H of S is not transmitting to the closed loop transfer function. Okay, so let us go with a simple example. So if say that from the generic diagram that we have, or say for the rate compensation, say the rate compensation one. So yeah, here it is. So for this one, say they have given you the two conditions that G2S is 1, okay, and it is a rate compensation. That means your KF HCS equal to KFS. Okay, so if you try to figure out what should be the value of G of S, H of S from this one, so then you can see that G of S, H of S will be okay. So K1 G1s from the generic equation that we derived previously. Then you have Kf HCS plus K G2s. So G2s is 1. So this is going to become 1. Now here you can actually take common of, and this one is becoming S. So what we are having here is if you take common of the Kf, so what is left is Kf K1 G1s, then you have S plus K by Kf. Okay, so what you can see here is another pole, another 0 is added. So 0 at minus K by Kf is actually we added with our G of S, H of S. Okay, previously H of S was 1, but now we have added this 0, and this 0 will be actually contributing for reshaping your root locus. So based on the value of K and Kf, basically we are going to reshape the root locus to obtain or to go through the desired point. Okay, so after doing that, once you know the value of K and Kf, you know the location of the 0 that is required to obtain for a root locus to go through that a desired point. So final thing is left is the value of K1. So you have to just adjust the value of the K1. This is the final thing, so that you can obtain your desired characteristic. Obtain desired characteristic. So desired transient response. So this is the simple idea of doing the thing. So now let us solve one problem, then step by step the thing will be clear to you. Even though it is slightly complicated than the cascade compensation. So example 9.7, example 9.7, example 9.7, it says that a particular uncompensated system is provided. So K1 by S plus 5, S plus 15. Okay, so this is the unity feedback system given, uncompensated system. And what they're asking you to do is, first of all, you have to implement a rate feedback control system, compensator. And at the same time, using that, what you have to do is your settling time that you are going to get, that has to be the new settling time, has to be 1/4 of your previous or old settling time. So this is one criteria. And you have to maintain 20% overshoot. Okay, so basically this will give you the constant zeta line. Okay, so this is the fact been given, and what you have to do is you have to implement the rate control. The configuration is also provided. So configuration says that you have to implement this. So the value of K is also given, which is 1, and then you have to have transfer function. I'm not writing it again. So this G of S will be coming here. Okay, so and then you have rate feedback, that is KFS, and your okay, so unity feedback. So this is how you have to do it. Now again, the idea is same. So what you have to do is, first step is always plotting the root locus for the uncompensated system. So the steps are similar to the cascade that we have done. So step one is always plot the root locus. Plot the root locus. So for plotting the root locus, I'm not showing it, but I'm just, I have already calculated. I'm just giving you the summary of the root locus, how it should look like. So the summary is number of the branches is 3. Number of branches 3, because you have only 3 pole. So number of infinite line 3. Then your sigma A, just calculate, you're going to find it minus 6.667, or and your theta A, 3 infinite lines, so basically 60 degree, 180 degree, and 300 degree. Okay, so then you have to figure out your the breakaway point. So breakaway point sigma 1 2, if you calculate. So I'm just giving you the result. So minus 11.076 and minus 2.257. So basically you are going to see that this one will be applicable. Then you have to find out the j omega axis crossing. So using the route table, so you're going to find that this is plus minus j 8.66. The problem is made in the book is that they have actually skipped so many things. It is actually difficult to understand what is happening there. So that is why very quickly I'm just showing you what you have to do. Okay, so after doing all of this, then you have to know what are the root locus should look like. Then also percentage overshoot is given. So for that percentage overshoot, you can find out the formula, and you're going to see minus ln that formula. If you apply, then you're going to find out that it is 0.456. We already calculated this so many number of times. So basically theta is cos inverse zeta, so which actually give you 62.877. This is also calculated. So the angle with the real axis, so theta with real axis maybe, you can find out 180 degree minus 62.877. So basically you can find out what is the angle with respect to the real axis. Okay, so all these are actually to finding your root locus, tentative root locus. So we know how the root locus which will be looking like. So you'll have at 0, at 5, at 15. So basically the 15 will be going in that direction. So 15 will be going in that direction. So this will be merging in between 5 and 0. So that is why we actually pick this value. Okay, so they'll be merging, then they will have a curve like this, something like this. So then you have to find out your zeta line, then you have to find out the intersection point. Okay, so after finding the intersection point, I'm just following it from the book. So since we know how to do it, so they have said that this is minus 1.809 plus j 3.531. Okay, so this is the step 1, just to plot the root locus and to figure out the current behavior. Basically, the location will give you the behavior. So now they ask you to figure out what should be the new value of TS. So basically, TS is 4 by sigma D. Sigma D basically 1.895. So from this one, because it is very much straightforward. So you don't have to repeat it, because of the fact that if it is 4 times lesser, then sigma D value have to be 4 times higher. So doing the calculation is actually not that necessary. So you can directly say that sigma D new definitely has to be 4 times sigma D existing. So basically 4 into 1.809. So basically it will give you 7.236. Okay. So once we know the sigma d, we can easily find out what should be the value of omega d. So omega d mu has to be tan angle. Okay, so sigma d times tan, because same zeta angle, so 117.129. So this is what you have to plot it here. So just follow the last class. So 117.129. So basically that will give you 14.12. So we figured out the point. The point is basically the new point that we are looking for is somewhere here, and the new point has to be minus 7.236 plus or minus, because the another point will be here. So plus or minus j 14.12. Okay, so once you know the new point, now you have to reshape your root locus. Okay, so for reshaping the root locus, you have to find out the angle contribution of the existing poles and the zero. So we know how to find out the angle contribution, isn't it? Zero angles minus pole angles. So basically, the angle contribution will be angle contribution. So you just have to apply the tan inverse from, because all of them are actually pole. So all of them are pole, so all of them will be negative. So negative tan inverse. Okay, so for this one, the pole value, so basically height 14.12 divided by 7.236. So similarly, you have to find out all the angles. So one thing you have to be careful is that, so if the angle is more than 90 degrees, then you have to actually subtract it from 180 degrees. So this one has to be minus 180 degree minus this value. Okay, so for the other two, so this one also has to be 180 degree minus, because it has to be somewhere here. Okay, so because if it is 5, then it has to be at 7, so it will be higher. So angle is still more than 90 degree. So if the angle is more than 90 degree, it is 180 degree minus that angle. But if the angle is lesser than 90 degree, then you can directly apply the tan inverse formula. So if you apply it, okay, minus, then what we are going to get is minus 277.33. So additional angle contribution, because we know that the angle has to be plus or minus 180 degrees, isn't it? So with this one, if we add 97.33, then it will be minus 180 degrees. So then that particular point will be on the root locus. So this value has to be provided by the zero that we are trying to add. Okay, so what is the formula? Again, the angle is more than 90 degrees. So whenever it is more than 90 degrees, so your formula will be tan 180 degree minus 97.33. Then height is always same, so 14.12. Then you will have 7.236 minus this. So you have to just be careful about whether to figure out ZC minus this or this minus ZC. So it actually comes from the angle. So if the angle is more than 90 degree, so this value has to be higher than this one. So basically now if you apply solve it, then what you're going to find is ZC location has to be 5.42. Okay. So we have to have a zero here, somewhere here. Okay, so now for the rate control system, so from this diagram, so we have to figure out what is the equivalence of it, because we want to know what should be the, we already figured out what is the location. So location has to be at minus basically 5.42, okay, so minus 5.42. So ZC location has to be minus 5.42. 42. So then how to find out what should be the transfer function here. So this is what we are trying to do. So for that we have to simplify it a bit. Okay, so we figure out what should be the value of ZC. Now we have to simplify this block diagram a bit. So what it is going to look like is K1 divided by S plus 5, S plus 15. Okay, and if you simplify the feedback one, then what you are going to get is 1 plus. So 1 plus KFS plus 1. So okay. So now you can take common of the KF. So slightly further reduction. We are not drawing this one remaining same. So only in the feedback one, KF you take common 1 plus 1 by KF. Okay, so this is what we are going to get. Okay, so this is how it looks like. So what you can find is basically here, if you want to plot it for the root locus, then what you are going to see is that we already find out what is the value of 1 by kf. So 1 by kf is nothing but 5.42. So from that one, you can easily find out what will be the value of kf, which is 1.185. Okay, so now if you plot the root locus of this one, this is your G of S and this is your H of S. So your G of S, H of S should look like this. If you multiply both of them, then you are going to find K1, KF. Then you have 0 at S plus 5.42. The 0 just you have calculated. Then you have the poles that at S plus 5, S plus 50. So now the value of K1, K2. So K1, K2 is nothing but the gain that we are varying for the root locus. So you can term this one as a K. Okay, so you can easily find out what should be the value of K. The value of the K is simple. The pole lengths, product of the pole lengths divided by the product of the zero lengths. Okay, so if you apply it, you are going to find that basically the distance from this zero and the distance from this pole of the new point that we figure out. Okay, so minus 7.236 plus J 14.12. Okay, so if you just put the value, Pythagoras, you apply, then you're going to get is 256.744. Okay, so K is 256.744. Actually, K has both K1 as well as KF. We already figured out what is the value of KF. So K will be K1 will be basically 256.744 divided by KF. KF is 0.185. So if you put the value, it will be approximately 1387.7. So I'm just following the book value. So 1388. Okay, so K1, KF is actually figured out already. Now, if you want to find out the steady state error, then actually you should go for the closed loop transfer function. No, actually unity feedback transfer function. So we already have this block diagram. So Then we simplified it as a feedback of this one. So now from this one, we actually have to figure out that how we can actually make it something like this. Okay. So you have to have a unity feedback because we need G equivalent S to figure out the error. So how can you do that? So the formula is very simple. The formula is forward path gain divided by 1 plus forward path gain feedback gain minus G of S. So if you apply that, then what finally we are going to get out of this is okay, so K1 by S square plus 20S plus 75 plus K1 KF. Then you have the unity feedback. Okay, so now as you can see, the type of this system is 1, so type 1 system. And because of the type 1 system, we have to go for KV. So KV is a limit, S tends to 0. Then you have G equivalent, S. Don't forget the S, it has to multiply with S. So S is getting cancelled out. What is left with is basically K1 by 75 plus K1 KF. We know all the values, so if you put the values, you're going to get something like 4.18. Okay, so whether you have noticed one thing or not, that is, we always say that the zero of the feedback will not go to the total transfer function. Okay, so this is evident from here. So if you just figure out what is TS, you're going to see that the zero is not going to come here. Okay. So finally, steady state error is 1 by kV. So you're going to get 0.239, something like this. Okay, so you can find out the higher order pole, using the formula. You can derive the formula, or you can find out the distance, or the trial and error that I have shown in the last class, whichever is suitable for you. So you're going to see that our higher order pole for that particular value of gain, so gain was K1 KF equal to 256.7. For that, you're going to see that our pole is at location sigma equal to my 5.53, so which is not 5 times away from not 5 times away from our dominant second order pole. So actually, even though we have done all the calculation, we cannot say for sure that the result that we have achieved will actually be satisfied without the simulation. So you have to draw the conclusion that these are the results after doing the calculation. So, but whether it is valid or not, for that you have to go for the simulation. And also you have to basically generate the table 9.8. Table 9.8. Okay, so I have just shown you the calculations, how to do it. And based on that, you have to design the whole thing. Now the second approach, approach 2. So approach 2, for that one, I'm not going to cover because we don't have much time. So I'm not going to go in detail in the approach 2. Rather, I'll just explain it from the book. what is happening in the approach 2. So as we already said, that approach 2 is basically designing both of them separately. So for designing both of them separately, what we have to do is actually, if you look at that transfer function of the generalized transfer function of your feedback compensation. So what we're going to do here is we'll be considering this portion feedback separate, and we'll be plotting one root locus for this one, and we'll try to figure out the design specification of this particular loop, and then this particular loop will be considered as a forward path gain for the whole transfer function. So basically two separate one. So in the first one, we'll try to figure out what is happening in this minor loop only, and then we are going to design the unity feedback, the whole thing. So pole and zero may not be necessary for this one. So what is mean by here is for one root locus, we'll try to find out what will be the pole location for this particular system. Then based on those pole, we'll try to design the overall transfer function or overall root locus. Let us see the example, then things will be even more clear. Okay, so now in the second approach, as we already said, separately we are going to design. So what it says is, okay, so example 9.8. So similar, same example as the previous one. Now this time we'll be applying two separate loop. So first loop is this one. We already moved the value k to the other side. Okay, so this can be the gain. So this one is shifted here. Okay, then we have simple, this is our g of s and this is our h of s. Okay, and in the minor loop, you have to maintain a damping ratio of 0.8, and in the major loop, we have to maintain a damping ratio of 0.6. Okay, so from g of s, h of s, which is in this case kf s divided by s plus 5, s plus 15. So based on this g of s, h of s, where your kf is the value that you're changing to find out the root locus. So gain is kf we have to consider here. And also, whether you have noticed or not, we have a pole at origin and we have a zero at origin. So they are actually cancelling each other. So this is one important phenomena that you should look for. Okay, so now look at the first portion of the design. So for the first portion of the design, we have to find out the closed loop transfer function. So this is the closed loop transfer function of your minor loop. Okay, so then the rest of the things as before. So you have to plot the root locus, and as you can see, we have a pole zero at origin, so their effect is nullified. Then you have one pole at -5 and other pole as -15. So basically, since their effect is nullified, so basically we can consider there is a two pole only. So basically, one will be merging, they'll be merging together at the middle. The one will be going upwards, the other will be going downwards. Now this pole here will be considered as stationary pole. Stationary pole. Stationary pole. Okay. So why it is stationary pole? Because we know that the zero that is coming from the feedback is actually doesn't go to the final transfer function. So for the final transfer function, this zero will not be available. But for the minor loop, the zero is available. So For the minor loop, this pole will not shift. So this is remaining stationary. But for the major loop, we are going to see that this pole is going to actually change its position. Okay, so similarly, you find the zeta line, then you find at the intersection point. So now the major loop, so minor loop is design is completed. So this is the value of the location that we want to have and for which value of kf. So that value of kf and these locations will be transferred as a basis for the next design. So basically one pole will be here, one other two pole will be here. So from here we'll start drawing for the major loop. Okay, so now go for the major loop. So major loop starts, we have three location, three pole, from where we actually stopped in the minor loop. So one pole is here, the other pole is here, and the pole at the origin. Okay. Now you have to, again, you have to draw the root locus, applying your, in this case, you have to also consider about the angle of departure. So that will give you the hints how to do it. And one will be going 60 degrees, one will be going 300 degrees, the other one will be going towards your 180 degrees. Now you have to draw that constant zeta line. So this is your, the intersection point is your closed loop location. So whether you have noticed the difference here or not is that here actually we have changed the gain of two value. So for minor loop, we have changed the value of gain kf. Then we find out the suitable starting point for the major loop. Then we have changed the value of k, and then we find out the intersection point, which will give you, which will give us the desired operating point. Okay, so no additional pole zero is actually introduced here. Rather, to separate root locus and to separate intersection point that we figured out. So the minor loop will be actually operating in totally separate condition than your major loop. Okay, so this is, and you actually have to figure out the table again. Okay, and then if you look at the table, so as you can see here as well, the dominant pole, second order pole, and the third order pole, they're actually not 5 times away. So you actually have to verify by the simulation again. Okay, so this is your feedback portion. Now, next thing that we have to see is physical implementation. Okay, so whatever the transfer function that we are seeing, how actually we can implement using the actual parameters. So for that, we have to take help of the chapter 2 again. So the chapter 2, we have studied that non-inverting amplifier, isn't it? So non-inverting amplifier. And that non-inverting amplifier was giving us a transfer function like this. So this is your Z1, this is your Z2. Okay, so this is your minus, plus, then you have your ground, then you have, this is V in S, this is your V0S. So we have seen that V0S by V in S was actually minus Z2 S by Z1S. Okay, so now if you have different values of Z1 and Z2, so say Z1 is, Z2 is a resistance R2 and Z1 is also a resistance R1. So then it is just a simple proportional controller. So basically minus R2 by R1. Okay, so, but if you have something else, like say Z2 is, Z1 is a resistance, Z1 is a resistance, and Z2 is a capacitance. Okay, so capacitance 1 by SC. So then what should be our transfer function, controller transfer function? So controller transfer function will be something like this. Minus sign will be always there. This is coming from the negative, also inverting amplifier because of that. So minus 1 by SC divided by R. So basically, if you take the constant away, so RC by S. So basically, at one pole at the origin, that is integrator. Okay. So now, say we want to have a PI controller. So for PI controller, what should be the value of Z1? So in Z1, you have to have a resistor and the capacitor in series. And for Z1 has to be a resistor only. So say this is your R1 and this is your R2 and C. Okay, so Z2 by Z1. So Z2 by Z1. So what is Z2? Z2 is R2 plus 1 by CS divided by R1. So if you simplify a bit, then what you are going to get is, don't forget the minus sign. Minus sign is because of the inverting amplifier. So what you are going to get minus R2 by R1. Then you have S plus 1 by R2C by S. So we said that in case of the PI controller, what you have to have a gain. So this is a gain. And then you have a pole at the origin and very nearby zero. So this is a very nearby zero. So you have to choose the value of R2 by 1 by R2S in such a way that the value of the location of the zero is very close to the origin. So this is the PI controller. Similarly, actually in the book, you have the whole chart and this is your table 9.10. So I'm just showing a few examples here. So for making PID controller, so PID controller, you go through that table 9.10. So now the PID controller, for PID controller, what you should have is Z1 has to be derivative. So Z1 has to be a parallel capacitor and the resistor network. So this is your Z1. So this is your C1. This is R1. This is your Z1. And Z2 has to be, just before that we have actually shown that it has to be a series resistor and capacitor. Basically R2, C2. So now you find out what will be Z2. Z2 will be R2 plus 1 by S C2S. And similarly, this one, you can take help of the admittance. So Z2 will be 1 by conductance, that is 1 by R1 plus C1S. Okay. So then you can finally simplify the thing. Okay, so you can simplify and Z2 by Z1 will eventually give you something like this. Don't forget the minus sign. Minus sign will be always there because of the inverting nature of the amplifier. So basically what we are going to get here is R2C. So the final one. R2 by R1 plus C1 by C2 plus 1 by C2 R1 by S plus R2C1S. So from the last class, we can, this is your PID controller. So one is proportional, okay. Then you have your integral, then you have derivative. So we have seen that K1 plus, the error is actually coming, then the error is multiplied by the gain K1. Then it is also multiplied by the K2 by S. Then it was also been multiplied by K3S. So all three was actually summing to figure out what should be our overall GC. So this is your GC. So we all of them actually adding together. So what you have figured out is K1 plus K2 by S plus K3S. Okay, so as you can see, this is K1 is actually nothing but this. K2 is this one, and your K3 is this one. So in one of the example in the last class, I think example 9.5, we designed a PID controller. So the controller gain was something like this: GS equal to S plus 55.92 pure. This is PD controller, and then you also have S plus 0.5 pole at the origin, and this is actually PI controller. Okay, this is PI, this is PD. That was the last class's design. So now if you just multiply those two and simplify to have a form like this, so what you are going to get is 56.42 plus 27.96 by S plus S. So from here we can conclude, if you compare this one with this one, we can say that R2 by R1 plus C1 by C2 equal to 56.42. And you have 1 by C2 R1 equal to 27.96. And your R2 C1 equal to 1. Okay, so 3 equation, 4 unknown. So how can we solve that? So you have to assume one particular value, then you have to go for calculation of the rest of it. So we can start from here. So say C1 is, okay, so you can choose any particular value of C1. But the book actually started from here, but it doesn't make any difference. You can start from here anywhere. But it is better to choose a value for the capacitor, because variable capacitor is not available in most cases. So we have to choose the predefined value of the capacitor. So say 0.1 microfarad or 1 microfarad, and based on that calculation you can find out what should be the value of R2 from this one directly. Then you can replace the value of C1 and R2 into rest of the 2 equation, and then you can find out what should be the value of R1 and C2. Okay, so this is how you have to figure out. Even though in the book they have assumed this one, then they figured out the rest of them. Okay, so eventually after finding out all of them, then you know how your controller should look like. The controller should be looking like this: minus plus. This is grounded, so inverting amplifier. So you have two resistor and the capacitor. So we already figured out what should be the value of the capacitor. So I'm just writing the book's value, even though they have used this one, then figure out the rest of them. So the book's value, according to them, is something like this: 0.1 microfarad, then 179 kilo ohms, then you have 358 kilo ohms, then you have 5.6 microfarad. So it will be difficult actually to find this one. Rather, we have to choose a value that is closer to this one. Okay. Now the last thing is the passive circuit implementation. Okay, so in the passive circuit implementation, basically instead of using the op-amp, you can directly implement using the resistor and the capacitor network, and that will give you actually lag, lead, or lag lead compensation. So for this one, the configuration is something like this: resistor, then you have a resistor and the capacitor. Okay, so for this one, you'll have something like this. You have to, so as you have noticed, for derivative term, actually you have to have a capacitor and the resistor in parallel. Okay, so then you have a resistor here. Okay, and lag lead, the combination. So both derivative and integral part will be there. So derivative is resistor and the capacitor in parallel, and then you have for the integral part actually, so resistor and the capacitor has to be in series. So okay, so just do the calculation, find out the table actually table 9.11. Okay, so we don't have much time, but if you want, we can go divide the lead compensator one maybe. So, and then you have to figure out the example 9.10. So how to figure out the value, just very basic. So again, compare your two equation, and based on that, it may happen that you have lesser number of the equation than unknown parameter. Then you have to assume few value. Then you finally could figure out what should be the rest of the value based on that assumed value. So this is the end of your chapter 9.